Okay, in this video we're going to start to cover section 4.7, which are optimization problems. And in this section we're just going to learn how to solve applied min and max problems. One of the most common applications of calculus involves the determination of minimum and maximum values. Consider how frequently you hear or read the terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least sized, greatest strength, greatest distance. Before outlining the general problem-solving strategies, we're going to just dive right into an example. You know, what we've done in the previous section is we've looked at some function, and we know we have min and max values. And you know, maybe there's a problem where you're in industry and you have a product that you want to box up and ship. And what you want to do is find the volume that you need to ship with, and you might want to minimize the cost by using as the smallest amount of cardboard possible. You want to play with the length, width, and height of the box to give you the volume that you need, while at the same time minimizing its surface area, which means minimum costs to build the box and ship the product. You know, this section has many real-life applications. And again, we are going to go over the general outline of this problem-solving strategy, but we'll sort of do that as we go through this first example. So in example 1, it says we're going to find maximum volume. A manufacturer wants to design an open box, you know, open top, it's got a bottom and 4 sides. This open box has a square base and a surface area of 108 square inches. So let me highlight that. That's one of our constraints. Surface area is 108 square inches. And this is shown in the figure. Which dimensions will produce a box with the maximum volume? So in this problem we have limited cardboard. We have 108 square inches of cardboard. We want to design a box that will give us the most volume possible. And we're going to do it with calculus. So where do we begin? We know that we want to maximize volume. We first want to find our primary equation. Primary equation. That's the equation that you want to minimize or maximize. So let's find the volume of this box here. Volume equals, and basically the volume is the area of the base times the height of the box. So in our box the base is square, its side lengths are x and x, so the base is x squared, and we're going to multiply that by the height of the box, h. So we have our primary equation. Again, that is the equation that we want to minimize or maximize. But the problem here is we have two different variables. Volume equals, we have an x variable and an h variable. What we need is a secondary equation. The secondary equation will have these same variables, x and h, but they'll be tied together in a different way. They won't be talking about volume, we'll be talking about something else. But we need an equation with these same variables that deals with this box. And the clue is given in the problem setup. It says the surface area of the box is at most, or it's going to be exactly 108 square inches. So what we want to do is come up with our surface area equation. You know, how many square inches of cardboard would we need to make this box? Well, first we'd look at the base of the box. You know, the base of the box is x times x, or x squared. X squared plus, and then we have 4 sides to the box. So we're going to have 4 sides. Each side is length x, height h. So x times h would give us 1 side. X times h is 1 side, and we have 4 of them. So we're going to have 4 and then x times h. And the surface area we were told is going to equal exactly 108 square inches. So our primary equation, again, is the one we want to minimize or maximize. Our secondary equation contains the same variables, but they're set up in a different way. Now we want to maximize the volume. So we want to write this v as the product of one single variable. So what we want to do is solve this secondary equation for either x or h, and then plug it back into the primary equation. So we'll have a single variable. And you know, we're used to dealing with x's. We have an x squared here. So let's take this secondary equation and solve for the h variable. We'll have h equals something, and we'll plug that something in for this h. So let's solve this for h. First thing we're going to do is subtract out an x squared. So we'll have 4x times h equals 108 minus x squared. And then we're going to divide by 4x. So we divide each side by 4x. So we're going to have h equals 108 minus x squared over 4x. This is h. Oop, and I meant to change that to a different color. So here is h. h is equal to this in the box. We're going to plug that in right here. So we're going to have volume equals x squared times, in a set of parentheses or brackets, this quantity. Let me see if yeah, I can just erase this. So our primary equation again was v equals x squared h, and we're going to plug in that new value for h. We had x squared, and we solved h was 108 minus x squared over 4x. And let's clean this up a little bit here. Let's distribute. We'll have 108 x squared, and then minus x to the fourth, all over 4x. And we see that every term has an x in it. So we can eliminate this x to the first, and that'll knock this down to x to the first power, and this will become x to the third power. And we do have this 4 divided by. Let's at least apply that to the first term. 108 divided by 4 is 27x. Minus, we have this x to the third over 4, or 1/4 x to the third. And this is our v, our primary equation. So we took our primary equation, and now we used our secondary equation to get it down to an equation with a single variable. We have v equals, and everything over there is in terms of x. Now, before we go any farther, we want to come up with a feasible domain that is related to this problem. What values of x make sense for our problem? Feasible domain. Remember, we only have 108 square inches of cardboard to deal with. At the very extreme case, what if we took all of our 108 inches and used it just to make the bottom of the box? So there was no height to it at all, it's just a flat piece of cardboard. That is the biggest we could make the base. And in that case, it would be x times x, or x squared equals our 108. And if we take the square root of each side, we know that x here would equal the square root of 108. And we should also think, this the base, it has to be positive. We're dealing with the area of something. You cannot have negative area. So somewhere, x is going to land between 0 and the square root of 108. Again, that's just our feasible domain, the x values that make sense for this problem. We can't have a negative base, and we can't go any more extreme than this. That's if we use every square inch of cardboard just to make the bottom of the box, and that would have a volume of 0. So, this is our feasible domain. X exists somewhere between 0 and the square root of 108. So what we want to do to maximize the volume, we want to find the critical numbers of the volume function across this interval. Our interval is from 0 to the root of 108. We want to find, mins or max values. In this case, we want max value. So we're going to apply what we learned in the previous sections to find our extrema, our maxes and our mins. We're going to find our maximum over this interval. So, yeah, let me just rewrite the interval up here, 0 to the root of 108. And I'll leave our primary equation right here, v equals this. Remember, to find mins and maxes, we need critical numbers. So we set our first derivative equal to 0. Our derivative with respect to x is dv dx, and that's equal to the derivative of 27x is 27, minus the derivative of this term will be 3/4 x squared. We want to take our first derivative and set that equal to 0. So the first thing I would do, I'm going to add this negative 3/4 x squared to both sides, and I'll have 27 equals 3/4 x squared. And then I'll multiply both sides by 4 to get rid of that denominator. So if we multiply through by 4 here, we're going to get 108, and that's equal to, these 4's will cancel, 3x squared. So 3x squared equals 108. If we divide by 3, we're going to get x squared equals 36, right? Yeah, x squared equals 36. And if we take the square root of both sides, we would get x equals plus or minus 6. Now remember, we're operating on the domain from 0 to 108. So the negative value makes no sense. We can throw that out. So the critical numbers were plus and minus 6. We can throw out the negative 1. And so now we have 3 points to consider. You know, our left endpoint 0, our right endpoint the square root of 108, and the critical number we just found of 6. So let me put this up here, x equals 6. We want to check the volume at these 3 points, the endpoint and the interior critical number. So if we do v of 0, we would get 27 times 0 minus 1/4 of 0 to the 3rd, or 0. Let's do the right endpoint, 108, the square root of 108. You know, I did this one on my TI-89. I put my function into the y editor, and I went to the table, plugged in this x value, and that spit out a y value of 0. So our last number to check is the critical number on the interior, v of 6. If we plug 6 into the original equation, we get an output of 108. So we know that to maximize the volume of the box, we need to use an x value of 6. And if we go back to the picture of the box here, you know, we can plug in a 6 for these x values. This would be 6 times 6. And we can go back to one of the other equations and solve for h. And in this case, it'll turn out to be a 3. So to maximize the volume of the box, given finite materials to build the box, we would want to make a box that is 6 by 6 and 3 high. You know, if we wanted to look at a problem like this from a more trial and error basis to find that maximum volume, we could just, you know, try out some different numbers. In that example, we should realize that there are infinitely many open boxes having 108 square inches of surface area. To begin solving the problem, you might ask yourself, which basic shape would yield the maximum volume? Should the box be tall, squat, or nearly cubical? You might even try calculating a few volumes as shown in this figure below, to see if you can get a better feeling for what the optimum dimension should be. Remember, you are not ready to begin solving a problem until you have clearly identified what the problem is. So our 108 square inches of surface area, we could build a box that was 3 by 3 by 8 1/4 tall, but that would give us a volume of 74 1/4. We could take another box and make it a 4 by 4 base, and that would leave 5 3/4 for the height, and that would give us a volume of 92 cubic inches. If we made our square base 5 by 5, that would only leave 4 3/20 for the height to give us our 108 surface area, and that would give us a volume of 103 3/4. We can see here that the volume is going up, 74 1/4, 92, 103. When we get to the box that we found with calculus, it was a 6 by 6 base with 3-inch height, and that gave us a volume of 108, a slight increase over this 103. If we keep making our square base bigger, if we jump out to an 8 by 8 base, leaving 1 3/8 inch for the height, our volume begins to drop back down, 88. You know, if we were to graph the function, the volume of the box would be on our y-axis, and the x values for our square base would be on the x-axis. This graph would look like a downward opening parabola. Oh, excuse me, it's not a downward opening parabola. If we go back to the original problem, our leading term is a negative 1/4 x to the 3rd. So a negative x to the third would go be coming down in the first quadrant and up here on the other side of the x-axis, somewhere in there. What we were looking for, there's probably a little bump in there. We were trying to find the maximum volume. You know, as we played around with different x values for the base of our box, we saw we were low, we got a little higher, we found the peak, we found the top of the hill, the max volume. As the base got bigger and bigger, our volume started to decrease. And now, you know, I said at the beginning there are some, guidelines to solving these type of problems. And here we got guidelines for solving applied min and max problem or optimization problems. First, identify all given quantities and all quantities that you want to have determined. If possible, make a sketch. Sketches sometimes really clear up the what's going on. Step 2, write a primary equation for the quantity that is to be maximized or minimized. A review of several useful formulas from geometry is inside the back cover of the book. We want to reduce the primary equation to one having a single independent variable. This may involve the use of a secondary equation, relating the independent variables to that primary equation. For number 4, we want to determine a feasible domain. That is, determine the values for which the problem you're working on makes sense. Step 5, determine the desired max or min values by the calculus techniques we've studied earlier in the chapter. We got a little note down here. When performing this last step, step 5, recall that to determine the max or min of a function or value of a continuous function f on a closed interval, you should compare the values of f at its critical numbers with the values of f at the endpoints. You know, the last example in this section is a really good one where we really want to pay attention to the endpoints of that interval, because the max or the min could occur at those endpoints. Okay, here in example 2, the directions say finding minimum distance. So which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? Well, let's figure out what this graph looks like. Our x squared term is at first, but it is a negative x squared, so we know it's a downward opening parabola. And if we set x equal to 0, we're going to get a y value of 4. So that's our y-intercept height of 4. If we set y equal to 0 and solve for x, would add x squared to both sides and get x squared equals 4, and the square root of that would be plus or minus 2. So we have x-intercepts at positive 2 and at negative 2. So we're starting to get an idea of what this graph looks like. Downward opening parabola, and we have its x and y intercepts. That gives us a pretty good idea. And the directions say which points on this graph are closest to the point 0, 2. So here's the point 0, 2. We want to minimize the distance between this point and the graph. So imagine we're going to have some lines coming out here. If we look at it way up here, that's a pretty long line. So that wouldn't be the minimum distance. If we come down way too far, this dotted line would be a lot longer than this one. We want to minimize and make that distance as short as possible. So, and they didn't give us any formula here besides this one. Is this what we want to minimize? Remember, our primary equation. The primary equation is the one we want to minimize or maximize. And this is the equation of our parabola. That's not what we want to max or minimize. What we do want to minimize is distance. So we have to think back to the old distance formula. And under the radical, we have x minus x1 squared plus y minus y1 quantity squared. Distance formula between 2 points. And in here, our given point is 0, 2. So we can plug that in for x1 and y1. So we're going to have our square root of x minus 0 quantity squared plus y minus 2 quantity squared. And let's just clean this up a little bit. Here in the first set of parentheses, x minus 0 is just x, and that's squared. Plus we have our second set of parentheses, y minus 2 quantity squared. So again, this is our primary equation the distance formula of which we want to minimize or maximize. In this case, we are minimizing that distance. But we have a problem. We have two variables, x and y. So we are going to need a secondary equation to get this one down to a single variable. And the only other equation we have right now is our given parabola, y equals 4 minus x squared. So let's plug this 4 minus x squared in for this y, and then we'll be down to a single variable. So our distance equals a big square root x squared plus this y value now becomes 4 minus x squared, and we still have our minus 2, and that quantity is squared. Let's just work in that second set of, or that set of parentheses under there. We're going to have x squared plus, and in our parentheses we have 4 minus 2 is 2 minus x squared, quantity squared. And what we're going to do is FOIL this out and collect up our like terms. So we're going to have our x squared plus, and then our first term squared is 4. We're going to have minus 4x squared plus x to the 4th. And because this is a plus sign out front, we don't have to worry about distributing a negative. That means our parentheses can just be dropped off there. Consequential to the problem. So here is our primary equation, and this is what we want to maximize or minimize. And we can still combine a little stuff on here. Let's see. We have an x to the 4th, and we have a x squared minus 4x squared, which is minus 3x squared plus 4. Now let's think about here feasible domain. In the last problem, it was an industry problem. We had fixed materials, fixed resources, 108 square inches of cardboard, and that constrained what type of boxes we can build. Now we're just talking about some graph on the XY plane. So in this case, it is possible that the minimum distance will be really close here. It could be way out, way down on the negative side of the y-axis. So here, our feasible domain is just going to be all real numbers. All real numbers. Anything can be into play, we'll check them all out. So there are no endpoints to check out. And now remember, we want to find the maxes and the mins of our primary equation here, this distance formula equals. And you see this radical and you think, okay, we're going to have to derive this. It's going to be a chain rule and it's going to get kind of messy with fractional exponents. But if we step back and think, we want to minimize distance, and our distance is given by this polynomial under a radical. If we want to minimize this entire thing, doesn't it make sense that we just have to minimize what's under the radical? So to minimize d, the distance, we just need to minimize what's under the radical. What's under the radical. If we minimize what's under the radical, that will minimize it even after we take the square root of it. So we can sort of just ignore that square root sign. We just want to take what's under it and minimize that value. So let's work on finding our critical numbers. And we're just going to take what's under the radical. X to the 4th minus 3x squared plus 4. And we want to minimize that. Let's just call this f of x. And let's find our derivative f prime of x and use that to find our critical numbers. Well, our derivative is going to be 4x to the 3rd minus 6x plus 4 derives off to nothing. If we set this equal to 0, we want to factor the left side. So let's see, we can pull out a 2x, and then we're going to be left with a 2x squared minus 3, and setting that equal to 0. Well, if we set 2x equal to 0, we get x equals 0. Now we're going to take what's in these parentheses and set that equal to 0. So we're going to have 2x squared minus 3 equals 0, and add 3 to each side. 2x squared equals 3. Divide by 2, x squared equals 3 halves. and then we're going to square root each side. So we're going to have plus or minus the root of 3 halves. Plus or minus. We're going to have plus the root of 3 halves or minus the root of 3 halves. There are our 3 critical numbers. 0, root of 3 halves, or the negative root of 3 halves. Again, in this type of problem, there are no endpoints to consider. Now from here, to figure out which of these are maxes or mins, of course we're only interested in the mins, we can do the first derivative test. Remember, we chop up intervals. We would go from negative infinity to the negative root of 3 halves. And then our next interval would be from the negative root of 3 halves to 0. And then from 0 to the root of 3 halves. And then finally from the root of 3 halves to positive infinity. And if we apply this first derivative test, we are going to find that 0 is a max. 0 is a max, and both of the radicals turn out to be minimum values. And that makes sense, from sketching our picture, and we want to be as close to this point 0, 2 as possible. It looks like, with the symmetry of a downward opening parabola, there are going to be 2 distances that are minimized, that are going to be points here on the parabola. And what we found are the x values of our minimums. So our minimum, we have 2 of them. First, we have an x value of the root of 3 halves, and the other one is the negative root of 3 halves. And to find the y values that go with these x values, we would plug these x values back into the original function, back into our original function f of x. Or back into the graph, y equals 4 minus x squared. And we'll find that they have y values of 5 halves. So this point here on the graph is the root of 3 halves, 5 halves. And here on the other side, we have a negative x value, the negative root of 3 halves, 5 halves. And of course, my graphic is kind of a sketch there. Let's pull out the one that came with the problem. Here's a much better graph. Again, we were trying to minimize these distances here. And we found our coordinates. Here it was the root of 3 halves, the square root of 3 halves, 5 halves. And our reflection into the second quadrant, where our x value would be